Hi. Today we're going to be going over question 5 of the spring 2023 exam 1 for communication systems and components. I'm Jake Sanchez. So let's get started. So a quick question explanation for the basics of this problem. What you need to understand is how to modulate a message signal, MFT, and the three basic types of modulation that we've been taught in class. Those are the DSB-SC, AM, and FM. So in here, this is basically the project description that I posted a picture of. So let's go on to part A. So part A deals with DSB-SC. So here we can see we're given our carrier frequency and our message signal. And the basic idea behind this modulation is that we multiply the message signal by the max and min of the carrier signal. And since the carrier signal is a sinusoid, we basically multiply by plus and minus 1, and we can graph the result of the multiplication with the message signal on the graph to the right. So here I'll demonstrate. So if I grab a pen, right, so let's make this our x-axis right here, right? So we have the from negative 0.5 is the message signal start. So let's put a line here that's a negative 0.5, and we'll make this one, right? And then it goes up to 3. So if we have 1, 2, 3, 1, 2, 3, right? So 1, 2, 3. This is going to be another one. 1, 2, 3. This is going to be 2, 2, 3, and this is going to be 3, right? So here we go up to 1, right? So we're going to go this way, right? And then we're going to go from 1 to 2 and down a whole level. So we're going to go like this. And then we're going to go from 2 to 3 all the way to 0. So like that, right? And that's the positive one. So now if we multiply by negative 1, we're basically going to have the flip of the signal. So you're going to go like this, and it's going to go down to negative 1, and then it's going to go to positive 1 here, and then it's going to go to 0 here. And the basic idea here is because the center frequency is 2 hertz, we're going to have basically 2 peaks in between each 0 to 1, 1 to 2, and 2 to 3, right? So we have from 0 to 1, let's go like this. That's 2 hertz, right? And here from 1 to 2, we're going to have 2 hertz again. So we're going to go like this. That's 2 hertz. And then from 2 to 3, we'll have 2 hertz again. So we'll go like this, right? And it's kind of hard to see, but all of those are 2 hertz in between, and that's the basics of DSB-SC. So let me switch back to, okay, perfect. So the explanation for this problem, here we have a DSB-SC demodulator. So we receive the signal G, right? And we multiply it by C of t, which is our carrier frequency, and we result in E of t. Now, E of t is basically the signal that we receive in times a cosine wave, which is essentially our carrier frequency, and it results in M of t times cosine squared, right? So we know from class that that's cosine squared can be put into the form 1 plus cosine times 2 times the frequency, and we have the message signal with half of the amplitude here. And basically we are able to, by putting it through a low pass filter, we can get rid of this component right here, and we can essentially create just the original message signal here, right? And this is just the frequency version of this. So here we can also see that this is a different example. So if we had a message signal like this, let's say this is M of t, we would basically do the same thing again for DSB-SC, which is multiply by 1 and negative 1 and put it onto a graph. And here is the carrier frequency. And we would basically just oscillate between the two M of t's, the negative, this one, and the positive, this one. and the frequency would go up and down and oscillate between the negative M of t and M of t. That's the basics for DSB-SC. That's the simplest one. So for part B, we're dealing with AM modulation. And the basic equation that we'll need to solve this problem is shown on the screen here. So it's mu is equal to MP over A. A good way to understand what to do in this problem like this, a good way to understand what to do in a problem like this on the exam is to remember, since AM means amplitude modulation, we want the amplitude to be the only thing that allows us to read from the signal coming in. So here we can see that they give us U equals 1/3, right? So from some simple math, we can obviously see that A is equal to 3, right? Since you have the fraction here, 1 is equal to MP and 3 is equal to A, right? So A is basically going to act as our offset. As before with DSB-SC, we still multiply by the plus and minus 1, right? So we're going to have a somewhat similar signal to the previous problem, where we're going to have this and the positive and negative here, or a better example is in here, we'll have the positive and negative. But in this case, since we have A equals 3, and we're doing amplitude modulation, we're going to offset this these plus and minuses by 3, right? So in this case, you have 0 is going to be this line right here. So you have negative half plus 3, which is equal to 2.5. So if you go up 1, 2 to here, so this goes like this, and this is going to be 1, let's say this is 2 here, and this one's 3. So here we'll go from the 2.5 that we have to plus 3, 1 plus 3, which is going to be 4. So we're going to go to here, and then we'll go from negative 1, which is this one right here, to plus 3, which is going to be 2. So we'll go to down here. So we go like this. And then we go from 0 here to plus 3. So that's going to be up to 3. So it's going to be up to here. Right? And we will have basically what is the opposite of this, the reflection of this on the other side. So I can just draw that in really quickly. Sorry. Oh, and then erase the entire thing. Right, so this is the resulting AM modulation, and what happens is with the frequency of 2 hertz, we will have, again, basically 2 cycles within every single period here. So we're going to draw on the 2 hertz. Sorry, it's messy. I suck at drawing with the computer mouse. And then we'll have another 2 hertz here, right? So it goes down all the way, up all the way, right? And then again here. Right? So all these points, these points should be touching the tops of the modulated signal. So for an explanation here, I drew this up really quickly beforehand. So we can see that the message signal here is just being added to some offset, which is A, and then being multiplied by the carrier frequency. On the right, we can see a different problem's results. And for the demodulation, of the actual signal, we can use something like like the square law, which is shown at the bottom here. And after passing through the low pass filter and the square root, we receive something similar to the original message signal we sent out. So what happens here is you get the received signal here, and you square it, and this will be the result. And after putting it through a low pass filter, this term right here will go away, and you'll be left with this. And once you put it through a square root, you will receive what you want, which is the original message signal. In this other example, it's the same thing that we did in the problem. You multiply by 1 and -1 on this message signal, so you get something like a DSB-SC. And then to make it amplitude modulated, you shift it up by an offset of A, and you receive something like this, which is the envelope for the signal. And then the envelope for the signal times the carrier signal results in the amplitude modulation that you see here. Okay, so part C. So part C, we're going to start with the calculations first. So here we can see that the carrier frequency is actually 1.5 hertz, which is important to keep in mind. And we're also told that the sensitivity, the frequency sensitivity, is 2 pi radians per second per volt, where m of t is taken to be in volts. So basically, the essence of FM is we will multiply by the frequency sensitivity, which is 2 pi, times the volts, which is, in our case, what our message signal is. So at 0, it's going to be negative 0.5, right? So negative 1/2, right? Which is equivalent to negative pi, which in this case is going to be equal to, if you change this from radians to frequency, it's just divided by 2 pi, basically. So then that becomes negative 0.5, right? So this is the offset that we want for FM. Now, when I say offset, I mean frequency offset. So from 1.5, right, from 0 to 1, this block right here, we're going to basically go from 1.5 to minus that. So we're going to go to 1 hertz, right? And what you have to do is calculate basically each period here, the frequency offset for each period, right? So at 1, it jumps up to 1.0, right? So you have 2 pi times 1, which is equal to, obviously, 2 pi, which is, in frequency, that's 1 hertz. So an offset of 1 hertz to 1.5, right? 1.5 plus 1 hertz is equal to 2.5, right? So that's where this 2.5 hertz comes, right? Sorry. And then you can see that it goes to -1 here, right? Which, if you just make that, that's going to be negative 2 pi, which is going to be -1 hertz, right? And then that's going to mean that it's 1.5 minus 1, which is going to be 0.5 hertz instead. So it goes to 0.5 hertz, right? And then from 2 to 3, at 3 it goes to 0. So that means that, well, obviously that would be no offset, because 2 pi times 0 means 0, right? So that would just be, again, it would be 1.5 hertz. That's supposed to be an H, sorry, hertz. Okay, so now that we have this information that from 0 to 1, it's 1 hertz. Starting at 1, it's going to be 2.5 hertz, and then it goes down to 0.5 hertz. And then from 2 to 3, it goes from 0.5 hertz to 1.5 hertz. We should be able to graph the problem. So here we'll write neatly what we want to say in mathematical terms. So 0 to 1, it's going to be, again, 1 hertz. So 1 hertz. And then from 1 to 2 equals 2.5 to 2.5 hertz, which is what we calculated. And then from 2 to 3, we will have from 0.5 hertz all the way to 1.5 hertz. Right? So indicate the beginning and ends of frequencies is very important here. So in our FM, you have to remember that there is no envelope in this case. So the carrier frequency, there's no envelope for the carrier frequencies to oscillate between. So instead, we're just going to use a sinusoidal wave, and the way that it conveys the message signal is by basically changing the frequencies, right? That's why it's called frequency modulation, obviously. So here we'll start with 0, then 1, and 2, and 3. I don't know if that's spaced out correctly. So from 0 to 1, you can see we have 1 hertz, right? So we're just going to have one sinusoid, right? And we want to label that. So that's 1 hertz, right? Make sure to label it because it's asking you to indicate. Then at 1, we go to 2.5 hertz, right? So here we go to 2.5 hertz and we slow down to 0.5 hertz, right? So we start at 2.5. And then we go down to 0.5. So obviously that you can't really draw that accurately, but we can label it here. So 2.5 hertz. And then here we are at 0.5 hertz. It's hard to draw with a computer. And then from 0.5 hertz, we go to 1.5 hertz. So from 2 to 3, we go from 0.5, which that should be increasing. So here, we have 1.5 hertz. Now, let me be clear. All of these amplitudes should be the same. I just suck at drawing. So the only thing that should be varying here, since it's frequency modulation, is the frequency between the peaks. So just to make that clear. And that's your answer for part C, as well as the calculations. The calculations should be very, very, very simple. So here we have an extra sample because FM is probably the most complicated one. So you can ignore the KP. That would be for phase modulation, which we don't do in this problem. So we can also ignore this 10 pi. So here we see that our frequency carrier is our carrier frequency is 100 megahertz, right? And we can also see that our KF, which is essentially our 2 pi radian, our frequency sensitivity, we can see that that's 2 pi times 10 to the 5th. So in our calculations, the first thing that we want to realize is this is our M of t. So there's only basically 2 major values here. There's -1 and 1, right? So we can just calculate 2 points and then go between them like this, right? So for +1, it would be this part right here, and for -1, it would be this part right here. And basically the calculation here is the 2 pi times 10 to the 5th, which is the KF, times your M of t signal, which is what we were doing here, right? But the only difference here is that we divide by 2 pi before, so we can just get it into frequency immediately. And we can see that we go to a minimum of 9.9 megahertz and a maximum of 100.1 megahertz, right? So our frequency should be changing between 9.9 megahertz when it's at -1, as you can see right here, or right here, and a maximum of 100.1 megahertz where it is right here. So if you draw like lines down here, you can see that at the minimums you have the lowest frequency, but at the maximums you have the highest frequency. So here would correspond to a 100.1, but here would correspond to a 99.9, right? And that's the basics of FM. Thank you. Please post in the comments if you have any questions.